So far in our journey about the concept of energy, we started by defining kinetic energy of a solid object without caring about its shape. It only depended on the speed and the mass of the object and was labeled EK. After that, the concept of gravitational potential energy was introduced and labeled EG. It involved the relative position of masses within a system. We then talked about the conservation of energy, namely the total mechanical energy labeled ET. This energy was described as being the sum of the kinetic energy and the potential energies, gravitational potential energy being the only potential energy discussed so far. To deal with the loss of total mechanical energy, it was recalled that solid objects are made up of molecules and atoms that can have individual kinetic energies and can change their relative positions and composition within the object. Thermal energy was not given a variable name, but the change of it was quantified by involving changes of temperature and states. All these types of energy were part of the scientific understanding by the year 1887, when the Michelson and Morley experiment took place. This experiment was meant to evaluate how fast the experimental apparatus was moving in respect to the medium that was disturbed by the propagation of light. It has been named the most famous failed experiment. It did not measure any change in the speed of light due to the velocity of the medium, and had to conclude that either the medium did not exist or that the experimental apparatus had no relative velocity in respect to the medium at all time. It was famous because it was the first hint that there was a big problem with the speed of light, and some revision of concepts needed to happen. In June 1905, Einstein had two papers published that offer such revisions. The first one introduced a corpuscular model for electromagnetic radiation, corpuscles that will eventually be called photons. The second paper was about the theory of special relativity that took as a premise that the speed of light, or any electromagnetic waves for that matter, traveled at a constant speed in vacuum for any observers. Because speed is a ratio of length and time, keeping the speed of one phenomenon constant had impact on how space, time, and energy were perceived. I will not go over the physics of space and time here. It is a subject for grade 12. But we will have a glimpse at the energy, especially how it relates to nuclear reactions. With nuclear reactions, our objects are, for example, nuclei, protons, neutrons, or electrons. Conservation of energy involves the concept of mass-energy equivalence, proposed by Einstein in that second paper. It does not mean that the mass is equal to the energy. It is summarized with the most well-known formula in physics, which is E equals mc squared. This equation is deceptively easy. However, it carries a lot of concepts. The capital E refers, of course, to energy. Notice the absence of a subscript. It is more like a total energy value for a combination of particles with mass. For a nucleus, capital E includes the kinetic energy of the whole nucleus and the changes of energy that went into combining these protons and neutrons together. It cannot be used to calculate the energy of a photon, which is a massless particle. The C in there is the universal constant that quantifies the speed of any massless particles in vacuum. It is usually referred to as the speed of light in vacuum, even though it applies to more than the speed of the photon of visible light. Its value is approximately 3 times 10 to the 8 meters per second. Lastly, m refers to the mass of the object. This m quantifies how hard it is to accelerate the object. It refers to its inertia. It is the m present in Newton's second law, F net equal ma. It means that if you exert a given force, F net, in the direction of motion of a given proton, the total energy, capital E, increases because the kinetic energy increases, but so does the mass of the proton, because the mass is proportional to the energy. It becomes progressively harder and harder to speed up this proton to the point that the proton would need an infinite amount of energy to reach the speed of light. So an object with mass does not reach the speed of light in vacuum. Only particles with no mass travel at the speed of light in vacuum. However, this change of mass with speed becomes important only when the object travels at speed close to the speed of light. At lower speed, the mass of an object is nearly equal to its mass when at rest, labeled m0. This justifies us using the rest mass as the mass of an object when mass was first introduced in these lectures. This rest mass leads to the concept of rest energy, which means that even when not moving, an object has energy. This rest energy is constant for a given combination of particles. Rest energies have been measured and tabulated. This new approach to define energy as E equals mc squared also modifies the concept of kinetic energy. Kinetic energy is the extra bit of energy that an object has above the rest energy when it is moving. In relativity, kinetic energy is defined this way. When an object travels near the speed of light, this new definition does not lead to the same numerical value as m0 v squared over 2, our old formula for Ek. However, for any small, everyday sort of speed, the relativistic kinetic energy has a value approximately equal to m0 v squared over 2, and it is usually good enough for a lot of applications. Now the question is, how do we use this energy stored in the rest mass of particles for our everyday needs, such as charging our phones? Let us look at this typical fission reaction that occurs in most nuclear reactors around the world. Here, a nucleus of uranium-235, which is not as common in nature as uranium-238, splits into barium-141 and krypton-92. You might be wondering why neutrons appear on both sides of the equation. Why not cancel one neutron, which would leave two neutrons on the right-hand side of the equation? It is because in this fashion, the sequence of events is more obvious. One wandering neutron is captured by one uranium nucleus, and the combination is so unstable that the uranium nucleus splits, releasing three fast-moving neutrons at the same time. These three neutrons could then meet a maximum of three other uranium nuclei that could each release three neutrons, and so on and so forth. Given the right condition of uranium density, these chain reactions could lead to the production of a bomb. Now, why would the products have more kinetic energy than the reactants? Let us look at the amount of rest mass of the reactants and the products. It is customary that the mass of nuclei and particles are tabulated in atomic mass units. One atomic mass unit is the mass of 1 over 12 of the mass of the carbon-12 atom, so approximately the average mass of one nucleon of carbon-12. Here are the value for the rest mass of one free neutron and the rest mass of one uranium-235 nucleus. We can similarly look up the rest masses of the products. Let's add up each column, remembering that 3 neutrons are present on the product side. As you can see, there is a drop in rest mass of the products compared to the reactants. This difference is called the mass defect. By conservation of energy, this drop in rest energy is matched by an equal rise in kinetic energy of the product compared to the reactants. In a nuclear reactor, the kinetic energy of the products is transferred to a moderator such as light water or heavy water that flows through and out of the reactor core. In most nuclear power plants, the heat from the moderator can be used to boil the water in a separate circuit of pipes, a circuit that is linked to turbines. The steam is used to move turbines, and the kinetic energy of the turbines is transferred to induced electrical current in transmission lines. Those transmission lines are ultimately connected to your home where you can charge your phone. The whole sequence starts with the nuclear reaction giving products with a lot of kinetic energy. Let us compare how much energy the previous nuclear reaction releases compared to a situation that we are familiar with, the boiling of water. If you recall from the lecture on energy consideration in change of states, the latent heat of vaporization of water is 2.26 megajoules per kilogram. The rest mass of a molecule of water is tabulated to be 18.015 atomic mass units. In order to work with joules, we need to convert the mass in U into a kilogram, which is approximately the mass of a neutron or a proton. With that conversion factor in mind, we get the rest mass of one molecule of water in kilogram. Now we can calculate the energy required to vaporize a molecule of water through this equation. Substituting the givens gives this value for the energy required to vaporize one molecule of water. Let us now look at how much change of kinetic energy occurred in the fission of one nucleus of uranium-235. This equation is based on Einstein's famous equation, where delta M0U is the change in rest mass between the reactants and the products that we calculated previously. We then substitute the givens, remembering that we also have to convert atomic mass unit into kilogram. The final value is 3.5 times 10 to the minus 11 joule. Notice that the energy released in the nuclear reaction is roughly 10 to the power of 9 times bigger than what is required to boil one molecule of water. In other words, the fission of one nuclei of uranium-235 could boil hundreds of millions of water molecules to run turbines. Well, that is if nuclear reactors were 100% efficient. The trick to extract energy from rest mass is to have products with less rest mass than the reactants. Let us see if it can be done with fusion by looking at the process of creating an alpha particle in the sun. It starts with two free protons with high velocities meeting and fusing. The protons need to travel fast or they would not be able to approach each other close enough to feel anything but repulsion because of their electric charge. The meeting of two protons creates an isotope of hydrogen that even got its own name, deuterium. In this fusion, one of the proton was turned into a neutron, and by beta-positive decay, a positron and an electron neutrino are also created. Later on, the newly created deuterium nucleus meets yet another proton to form an isotope of helium, helium-3. A gamma ray is also shed in the process. These two steps can be repeated with other protons and eventually two helium-3 nuclei can meet and fuse to form the helium-4 nucleus, which is our good old alpha particle. 2 protons were released at the same time. Let us write a net reaction for this process. In order to have 2 helium-3 nuclei for the step 3, we need the step 2 to be repeated. To get the 2 deuterium nuclei in step 2, we need to double the first step. We are ready to add the equations. There are 6 protons on the left side and 2 protons on the right side. This leaves a net 4 protons on the right side. The alpha particle only appears on the right side. The 2 deuterium nuclei and the 2 helium-3 are created and then used as reactant in their next steps. The positrons, the electron neutrinos, and the gamma rays are still present as products. As we have done before, let us look at what happened to the rest mass. On the reactant side, we have protons. There are 4 of them, for a total mass of about 4.029 atomic mass units. The product side includes the alpha particle, positrons, and electron neutrinos. For decades, a hot scientific question had been whether or not neutrinos had mass. It was experimentally found that they do, but it is very small and not very accurately measured. I am giving here an upper limit. It is so small that I will not include it in the sum of the rest mass of the product. Notice that the gamma particles are not present in the list for the rest mass because, being photons, they do not have rest mass. Now let us evaluate the total rest mass of the products, taking into account the number of positron and electron neutrinos in the equation. As you can see, the process of creating an alpha particle involves a loss of rest mass. This loss of rest energy was used to increase the kinetic energy of the products and to create 2 gamma particles, which are packets of energy. As an aside, not all fusion reactions lose rest mass. An evaluation of the rest mass for the first step would show a gain of rest mass at the expense of the kinetic energy of the protons. The reactions that were presented so far only involved a small loss of rest energy compared to the total rest energy of the reactants. There is, however, a type of reaction where all the rest mass of the reactants is used up, and it occurs when a particle meets its antiparticle. The most common reaction is the one between the electron and the positron. They completely annihilate each other, and 2 gamma rays are created, flying off in totally opposite directions and transporting all the energy of the former electron and positron. This reaction has an important medical application with PET scan. PET scan refers to positron emission tomography. It involves injecting a radioactive tracer into a patient. An example of a tracer is 18F-fluorodeoxyglucose. This compound includes an atom of fluorine 18. This isotope of fluorine has a short half-life of 110 minutes and needs to be created by bombarding protons onto oxygen-18 atoms. Afterwards, it is chemically attached to something similar to glucose. The short half-life means that the making of the tracer must occur in facilities close to the scanner. The injected tracer decays in the tissues of the patient through a beta-positive decay that creates the stable oxygen-18 and a positron. The positron does not need to go very far before meeting an electron and creating those gamma particles. The scanner consists of gamma rays detectors installed all around the patient. The scanner uses a computer which is looking for near simultaneous events of pair of photons traveling on opposite side of the patient's body. Cancerous cells use the glucose more than healthy cells, so the tracer will congregate more in cancerous tissues that can be located with the intersections of the paths of the pairs of gamma rays. This concludes the unit about energy. The next unit is about the physics of waves, starting with the definition of a wave.